Thanks, Alex. Welcome everyone to the first science seminar series of the winter semester of 2025. Talks are going to be happening every week, every Friday, 2:30 p.m. in this room now. On this note, next week's talk on the 31st of January will be given by Janina Bellini Sabini. I'm sorry.
I will be asking her for a phonetic pronunciation of her name. I know her first name is Shawnee.
Okay.
I don't know how to pronounce her last name though. I've never actually.
All right.
Yeah.
She'll be giving a talk from our Open Science. The talk will be on advancing research with open science and will be given via Zoom as well. For today's talk, we're pleased to have with us Dr. David Lobb, a professor of landscape ecology from the Department of Soil Science, University of Manitoba. Dr. Lobb is originally from Southern Ontario and earned his Bachelor of Science from the University of Toronto, with his postgraduate training at the University of Guelph. Dr. Lobb is internationally recognized for his work in tillage translocation and tillage erosion, with his expertise being sought by both national and international organizations. Dr. Lobb was also inducted into the Canadian Conservation Hall of Fame in 2015. And Dr. Lobb's talk today is titled Recent Advances in Soil Erosion and the Necessary Improvements to Soil and Water Conservation Programs and Practices in the Canadian Prairies. And following the presentation, there will be some time for question and discussion from both in the room and on Zoom. So please join me in welcoming Dr. Lobb.
Thank you very much. Thank you for inviting me to present today. I'm glad there's quite a few people there. And I wish I could have been there in person, but we had a Candice exam that had to get shifted and it didn't leave me enough time to drive there. And given the questionable weather, maybe that's not such a bad idea to stay here and give it virtually. And I have to make a comment on the presentation. It says recent advances. Now, recent for Alan Millennials on the presentation and myself is different than maybe many of you in the room. This is a commentary on recent advances in a decadal sense. For people like Alan Mullen and I have been working in soil conservation for 30 plus years, 40 years. That is actually recent. Soil conservation research has been going on for 100 years. It's one of the most developed and oldest areas of research within agriculture and certainly within environmental science. So the recent is a commentary on things that have happened in the last 2 or 3 decades. And it may seem like a long time to you, but there is a bit of a political commentary that even with 2 or 3 decades, with all the things I'm going to present to you, very little happens in a political and programming sense. There's a lot of almost glacial speed in the evolution of programs to follow science. Anyway, it's a bit of commentary, but that's why I say recent. So I'm going to highlight some of these recent advances in soil erosion and the consequential necessary improvements to soil and water conservation programs and policies and programs and practices in this region more specifically, but this applies globally as well. And I have to say that this presentation, if I can get it to advance now on me, there. Yeah, this presentation was originally given with a collaborator, Dr. Li Sheng, with Ag Canada in Fredericton now, but he was a PhD and a postdoc working with us at the U of M. We gave this presentation at the United Nations FAO Global Soil Partnerships International Soil and Water Forum in December in Bangkok, Thailand. So some of this information is very global in its context, but it also very much applies to this region.
Hey, David. Never mind.
Yep. What's wrong?
I'm certain if these slides are advancing, but they are.
Oh yeah. Well, there was the first 2 slides with the same slide. I just had different text associated with them. So, okay, back on track here. So there have been 2 major advances over the past few decades. And again, that's recent. And they are transforming the science of soil erosion and sedimentation across Canada and around the world. And both have a very strong connection to Manitoba, which is quite notable for the grad students in that room. The first is the use of Fallout-Radionuclides, or FRNs, to assess soil erosion and sedimentation. That's the first big one. In particular, the use of cesium-137, which, interestingly enough, is highlighted in the National Geographic magazine back in 2016. So this image is an excerpt from that, where they were highlighting some of the environmental advances. Cesium-137, which Alex and I have used a lot, and so has Alan. Cesium-137 is produced by thermonuclear reactions. Some cesium-137 has and continues to be produced by nuclear accidents around the world. Some of you may have heard of Fukushima in Japan recently, about Chernobyl, and there's a long history of nuclear accidents releasing a number of radionuclides into the atmosphere. But the majority was produced during the nuclear weapons testing back between about 1958 and 62, with a peak about 1960. And some of that bomb testing, the most notable is probably the Bikini Islands testing of bombs back in about that time. I'm not sure which year that was, but it's around 58 to 60. Cesium entered the atmosphere, was distributed around the globe, not uniformly, but it distributed around the globe through the atmosphere and was eventually deposited on the Earth's surface. And as such, it's considered a fallout radionuclide. It's one of many fallout radionuclides, of which some of us use. We use some of them in environmental science and agricultural sciences. Cesium binds strongly with the sheet silicate clays at the Earth's surface, the clays in this topsoil, more specifically, we refer to. The preferential fixation is the result of isomorphic substitution with potassium, and some of you may have heard of that if you've taken any kind of geochemistry or soil chemistry. It's the classic example of isomorphic substitution, where cesium pops potassium out of the sheet silicates. And in a practical sense, it acts like a paint on the land surface, allowing us to use it as a tracer for the movement of eroded soil. The losses and gains of FRNs, cesium-137 specifically in this case, allow soil losses and gain to be measured so we can quantify it, and they can be tracked to quantify sediment transport and fate. And this is a bunch of what Alex is currently doing. FRNs provide the most accurate means of assessing soil loss by soil erosion and sedimentation at a landscape scale and a watershed scale. Some people debate this, but I contest that it's by far the most accurate means of doing so. And these fallout radionuclides facilitate the assessment across scales from hill slopes to fields and up through the progression of small watersheds up to extremely large watersheds such as Lake Winnipeg and the Nelson River Basin. And Masoud Golharaki, who presented, I think, last year, Alex, he's been working on this using radioisotopes to track sediments and nutrients through the whole Nelson River Basin system. Their use has been critical for the validation of models of soil erosion sedimentation. And I just want to make a note here. Obviously, this diagram is in the National Geographic, but it was developed and provided by the FAO. And the International Atomic Energy Agency and the FAO, both of the United Nations, have been extremely important in the development of these techniques, all the way back to about 1980, when someone like Elcha de Jong at the University of Saskatchewan was one of the pioneers in all of these techniques. Alan probably remembers Elcha. And I would also like to say that NSERC has been very important in supporting the research that I've been doing and others in Canada, and certainly Ag Canada and Environment Canada have been extremely important in funding many of the research applications we've done with these isotopes. Our own research program, in our own research program, we've used FRNs in numerous studies across Canada and other parts of the world. And this map shows what you can see in North America. And this is just our research. There's many other people that have done research using these, but this shows many of our studies using FRNs to assess soil erosion and sedimentation. And it's I did a rough calculation, it's over 100 field sites in the past 30 years that have been done by me or through my lab. The second advance is the recognition of the process of tillage erosion. I think this is easily the only other major advance in soil erosion and soil conservation in the last 30, 40 years. And this process is separate from wind and water erosion, and much of the research in tillage erosion has been carried out in Canada, again with the support of NSERC and Ag Canada. And I'm going to give you a short explanation of what tillage erosion is, because I'm not sure how many of you have heard what it is. And I'm going to start with a bit of background on soil erosion, because it's always interesting to hear about soil erosion. Degradation by soil erosion is widespread in cultivated topographic complex landscapes, such as the one you see behind us, or in front of you, I guess, across Canada, North America, and around the world. These three images are from Minnesota, Manitoba, and Saskatchewan. Soil erosion is considered to be the greatest threat to our soil resources and their continued use for food production and how they affect the environment. This was stated back in 2015 in the United Nations Status of the World Soils Report, and we're currently trying to finish up the 2025 report. And again, in countries around the world, or regions around the world with many, many countries, again, soil erosion has been stated as the #1 threat to soil productivity and continued use. So it's quite important. These lands that I'm showing you here, these lands are what we would consider to be moderately to severely eroded, pretty common, very conspicuous in the prairies. We have black soils, typically thin black or dark brown soils over light colored parent materials. And the organic rich topsoil is lost from the hilltops and the subsoil is exposed, as is shown in this particular image. The consequence is a great increase in the variability of soil biophysical properties and processes. As you can imagine, crop production is one that farmers are interested in, but a whole bunch of processes like greenhouse gas production. Things that affect pesticide fate we've looked at, water runoff and water quality. Typically, with respect to crop yields, typically about 30 to 70% of the crop yield losses occur on about 15 to 30% of the field area, resulting in about 5 to 15% loss in gross revenue. So on an economic sense for agriculture, it's quite significant. The predominant pattern that you see in these images cannot be explained by wind or water erosion alone. This has been a contentious issue where people have said, oh, this is just wind erosion. Well, it's not. Those patterns cannot be explained. But tillage erosion is certainly the predominant cause of the patterns you see in these images. And so what is tillage erosion, to get a little bit deeper into that? Well, tillage erosion is the net redistribution of soil resulting from the variability in soil movement by tillage. Now, as you move soil around by tillage, you end up with variation in how much you move, as illustrated here, with the length of the arrows or the thickness of the arrows representing distance or mass. And as you vary them, you end up with losses and accumulation. Increase in soil movement, either a distance or mass, creates a net loss, and decreasing soil movement creates a net accumulation. And in topographically complex landscapes or hilly landscapes, like I'm showing you in the images here, the variability in soil movement by tillage normally results in the progressive downslope movement of soil, which is like a conveyor belt. You move soil around, it progressively moves to the bottom of those hills. So it results in soil loss from convex landscape positions and accumulation concave landscape positions, as shown here. And it doesn't really matter which direction you go. If you're moving soil under the influence of gravity, progressively it moves down slope, as any mass would. And it's particularly an acute problem on steep land. So not necessarily what you see around the prairies, but when you start to get out of the prairies in other parts of the world, like Southeast Asia, where you're in Central and South America, where you're farming on steep land, the soil moves down even on those, even though you don't have hills like we think of it, but those linear sections of land, soil does progressively move down slope. It doesn't matter what form of soil movement you have. If you move soil under the influence of gravity, it moves from the top of the slope to the bottom, and you end up with patterns as I've tried to illustrate here in this diagram. Now, a little bit more on this. So tillage erosion is a function of the erodibility of the landscape and the erosivity of tillage. So there's two general factors that affect the severity of the soil erosion. And this is similar, these terms are similar to what we use when we talk about wind and water erosion. We talk about the erosivity of wind or erosivity of water and the erodibility of the soil and land conditions. Now, landscape erodibility specifically is a measure of the intensity of hill slopes. And this is a site from Saskatchewan. You can tell it's pretty darn hilly. That would be what we consider to be fairly intense in terms of having lots of hill slopes. And land with many short, steep slopes is highly sensitive to tillage erosion, such as the hummocky landscapes I showed in the previous slide. It's considered to be highly erodible. And this is in contrast to water erosion, where long, steep slopes are the ones that are most erodible by water, and long slopes in general are most erodible to wind. In this case, it's short, steep slopes that are the problem, or the biggest problem. Cropping and tillage systems that employ intensive tillage, that's frequent, deep, or fast, can cause severe tillage erosion. They're highly erosive. So in other words, they're moving more soil around more aggressively. And tillage erosivity is a measure of how much and how far the soil is moved. And that's why I used those arrows earlier, showing the length of soil and the mass of soil by the length and thickness of the arrows. It's how much and how far that's moved. And that just represents movement. What is particularly important is the degree of variability in either how much or how far. That's where you create that net soil loss or net soil accumulation. It's the variability. And the tillage erosivity is a function of a number of factors, and I just detail them out here. One of the obvious ones is the implement design. Something that's very aggressive in its shape, arrangement, or combination of tillage tools is going to move more soil and potentially cause more erosion. Implement operation, the depth and speed of the equipment as it's pulled through the soil is extremely important for understanding how much soil, how far it's moving, and how variably. There are a couple of human factors here, which is quite different from wind and water erosion. It's important what the match of the tractor and implement is. In terms of the power availability and the power required, that determines that variability in soil movement and decisions made by the operator. So the behavior of the operator is also considered the significant factor. And these two human factors, we don't really know that much about. There just hasn't been enough study to really understand how much they control tillage erosion. We have a lot of anecdotal evidence. I've seen lots of it to suggest that it is very significant. Farmers can do very different things depending on what their beliefs are or how they operate, and that can result in very different outcomes in terms of erosion. So in our research, we found that tillage erosion results in severe soil loss, typically about 20 to 100 tons per hectare, so about 10 times the amount you would get by water erosion, on large areas, as I said before, 15 to 30% of cultivated landscapes. So you can get fairly substantial amounts of land area that are subject to moderate to severe soil loss. And it's pretty safe to say that tillage erosion causes more soil redistribution with some landscapes than either wind or water erosion. And that's borne out by work that we've done with Fallout-Radionuclides, looking at soil erosion by all processes. So it's quite significant. In terms of the processes, tillage erosion acts as a delivery mechanism for water erosion. So you can't really think, and I'll make this point later, you can't really think of wind, water, and tillage erosion separately. They're all operating in these landscapes. And tillage erosion acts as a major delivery mechanism for water erosion. It delivers soil to the convergent areas of a landscape where overland flow concentrates. So if you look at this photo on the image right here, this is from Indian Head, Saskatchewan, you can see where there's these thalwegs or these areas of concentrated flow where you get rills forming, these little sediment fans, and you think, oh my gosh, there's a lot of water erosion there. But it turns out that in those areas, you still have a complete soil profile. Where you get the soil losses on the hilltops adjacent to those water runs. And that's because tillage erosion scrapes topsoil off those hilltops and puts it right into those convergent areas. And we've seen this in Minnesota, we've seen it in Manitoba, we've seen it in Saskatchewan here. And it has part to do with our climate. If you move to a much more hydrologically active climate with a lot of water erosion, like in New Brunswick, where Li Sheng's currently working, you actually have as much, if not more, water erosion than tillage erosion. And those two processes combined completely degrade the landscape. So it's quite important to realize that the tillage erosion is a significant delivery mechanism for water erosion. Obviously, tillage erosion exposes subsoil, which is highly erodible to wind and water erosion. You can see that, and you see that in my next slide. And one of the contentions we've had, particularly when we're trying to wrap up this global stuff, some people say, oh, well, tillage erosion doesn't exist. Well, it turns out the similar findings to what I've just presented here have been made in 96 published studies from 39 countries around the world to date. And I have to, again, refer back to my first significant research finding. The use of FRNs was absolutely critical to making all these observations. Almost all of these studies have employed Fallout-Radionuclides to assess total soil erosion and therefore contextualize tillage erosion within total soil erosion. Okay, and the last point about tillage erosion. Tillage erosion can result in a tremendous amount of loss in soil productivity and crop profitability. This is what really drives interest, particularly in the agriculture community, around soil erosion in general and tillage erosion specifically. In such eroded landscapes as I've been showing you, it's estimated to be responsible for about 10% loss in crop yields and revenues over the field. Therefore, much more than 10% of the crop profits. So a small amount of gross revenue can result in quite a huge amount of net revenue or profit. And again, I just want to emphasize how important some of these advances are. These advances in research have transformed how we think about soil erosion and sedimentation, again, within landscapes and within watersheds, and how to manage these processes. Going from a rather basic illustration of what we thought the erosion processes were and how they operated over scales, we have a field operating as a black box that loses soil by water erosion, and that sediment travels straight downstream with only a small portion eating the terminal or reaching the terminal water body, like Lake Winnipeg. It's now developed into rather sophisticated recognition of it. It's a very sophisticated system of processes operating over topographically complex landscapes or surfaces within fields. It's no longer considered to be a black box with just water erosion resulting in the exit of or delivery or export of sediment. It's actually a combination of wind, water, and tillage erosion operating over landscape scales, over landforms that we typically characterize, as I noted here on the left-hand side, as lower, middle, and upper slope positions and depressional positions. If you look at those complex landscapes, there's a lot going on in the field, and only some of it, a small amount actually leaves the field by water erosion or by wind erosion, which I've tried to note here. And it will also move downstream in a much different fashion than what we used to believe. And one of the things that Alex has looked at and others have looked at since is the continuity of these processes. We now recognize these watershed systems are actually a complex series of reservoirs and conduits for moving water, sediment, nutrients, and they're very discontinuous. And there are many sources of material all along the pathway that actually can have more of an impact than what comes off the field. So that's quite a revolution in how we understand these processes to go. So hopefully, looking at this diagram, you get some sense that this is a rather sophisticated process or system with a lot of processes involved. Okay. So looking at the necessary improvements to soil and water conservation practice and programs. This is the so what part of it. What have we learned, and what does this mean about what we do about this soil erosion that is so problematic? I've identified 4 critical needs, and there's a whole suite of them, but I've just identified 4 that I thought they're most important. And I took this to the United Nations and said, these are the 4 things that need to be done globally, but also, I would argue, within Canada. And I'll illustrate some. There's some really interesting illustrations from Canada. Okay, the first one, we need a new understanding of tillage practices and systems. What we describe as tillage and how we describe tillage systems are based on what we learned in the 1960s and 70s. It has not changed. When we talk about no-till or conservation tillage or conventional tillage, it is very much based on what we understood them to be back in the 1960s and 70s. It has not advanced. And the problem is the technology has gone through a tremendous amount of change in terms of operations. And I've just illustrated here. This is a zero-till implement, very similar to what we'd have for high disturbance cedars in the prairies. And that is moving a lot of soil. That's not considered to be tillage. But in any definition of modeling exercise that's done elsewhere than Canada, that's not tillage. And you have a piece of equipment on the right there, which is vertical tillage. And that's not considered to be part of tillage. And many farmers don't consider that to be part of tillage. Our family farm got sold, and it had been no-till for 35 years. And the person that bought it kept it in no-till. But his definition of no-till includes a piece of equipment just like this. He's going over the field or ripping the crap out of it. But because it's not plowing and cultivating and disking like we thought of in the 60s and 70s, he figures it's still no-till. And because of that, there's a self-interest there that you can apply for conservation programs. So there is a bunch of politics involved in that, but there's certainly a problem with how we understand and represent tillage practices and systems across this country and around the world. So there's very much a need for a new understanding. There's also the complication that when you look at tillage erosion, this is, again, why tillage erosion is so important. Tillage erosion, which is quite evident to me in these 2 photos here, you can get conservation tillage systems that leave a lot of residue on the surface, but they also move a lot of soil, a lot of variability. And because of that, they may reduce wind and water erosion, but they may actually increase soil loss by tillage erosion. And that's a bit of the conundrum of how we look at these systems. You have to think of conservation tillage not simply being residue cover, but it's how much soil you move and with how much variability. And probably the most amazing, and there's something on the next slide, maybe I'll put the next slide up and I'll talk about that. These post-seeding practices can be more erosive than the primary and secondary tillage practices together. The one example we have, which is particularly acute, is potato production. On hilly land in New Brunswick, as an example, we found that the soil moved and the erosion caused by variable soil movement by hilling and harvesting potatoes was 3 times more erosive than all the primary and secondary tillage combined, all the plowing and disking, etc. So extraordinarily erosive, but it's not considered to be tillage. Again, that means you have to really rethink what you consider to be tillage and the consequence of soil disturbance in general. Okay. And the other one is cedars. We also did a study in Manitoba and Saskatchewan looking at high disturbance cedars and found that the high disturbance cedar can be as erosive as a moldboard plow, which is considered to be the icon of bad soil management. It moves a very small amount of soil, but it moves it at such high speed and with such high variability that the net movement, that variability I was referring to earlier, can be as much as a moldboard plow, which moves a lot of soil, but very short distances and typically with very little variability. So it's complicated. The second realization here is that we can no longer assume that practices that protect against wind and water erosion protect against soil productivity. When I started my work, and Alex, I'll pick on him because he's a little older than me, back in the 70s, certainly, we were sold the bill of goods in soil conservation that if you protect soil conservation, or conserve the soils, protect the soil, you'll protect the water, and all the water problems will end. And we were told if you come up with practices that reduce soil erosion by water and wind, you'll protect the soil. And that has been, it's still largely considered to be that way all across North America. But we are starting to realize that is absolutely not the case. The major source, a major cause of the severe soil losses that are affecting the landscapes, like you see in the upper left, those are caused almost exclusively by tillage erosion, not by water erosion. The processes that are causing that water erosion seen in the bottom right are much more complicated than that, and they're not necessarily related to anything going on in the field. And that particular image that I'm certain Alex remembers, that's at Miami, Manitoba, just to be clear about that. And that's showing the sediment coming out of the South Tobacco Creek watershed. And you can see there's a tremendous amount of sediment flowing out of that system. At the same time, the water that was coming off the fields up in the upper part, the cultivated fields where we assumed soil erosion was occurring, was coming off clear. The sediments were actually being generated through channel incision as water is flowing over the escarpment and through the various valleys. It was not coming from the farm fields. So there is a real disconnect between water and water quality and the processes affecting it and soil quality, soil productivity. And that's an extremely important distinction, that disconnect between those two interests. Thirdly, protection of soil conservation is not restoration. This is another contentious issue that people have to come to grips with. Soil conservation efforts such as conservation tillage may reduce soil losses, wind, water, and tillage erosion, and that's fantastic. So you want to stop soil erosion. But that does not necessarily mean that the soil is all of a sudden going to rebound. It will not restore the health and productivity of the soil. And there's a couple of reasons. Because you're not going to accelerate weathering on those areas to cause new soil to be formed. And the other problem is where we think we're getting restoration from is largely plant biomass, organic matter inputs into the soil. The problem is those severely eroded areas are very ineffective at growing crops, let alone sequestering organic matter into the soil. They're just not productive. They will not be effective. You cannot rely on simply stopping the soil erosion and assume that the crops you're growing on there are going to repair or restore the soil. It just won't happen. To do that requires some extraordinary efforts, such as dramatically increasing the biomass. And that becomes a problem because you need the water on the hilltops and the nutrient on the hilltops, which you don't have, and need the topsoil up there, which you don't have, to produce the biomass that you're hoping to achieve to actually restore the soil. So it's very problematic. So you can import material in, and some farmers in Manitoba do a lot of things like put extra manure on the hilltops, and that may not be a bad thing, but it's not necessarily a sustainable thing, and it's not necessarily going to achieve the restoration they're hoping to get at the rate they're hoping to get it. One practice that is of interest, and Alan Mullen, who's on the call, has been involved in this in the past, and Steve Crittenden, who's also on the call, is also engaged in this currently with a graduate research project with Curtis Cavers through Ag Canada, looking at soil landscape restoration. And one practice you can use to dramatically accelerate that restoration or repairing of the damage of eroded soils is simply by returning that eroded topsoil back up to the hilltop. In the practice, we refer to it as soil landscape restoration. Now, this practice is only possible because tillage erosion is the primary cause of the soil redistribution. In other words, the soil that's lost from the hilltops doesn't wash or blow away from the field. It just accumulates at the bottom of the slope because that's the way gravity works. So it's available to move the soil back up. And so this may seem like a little bit of an oddball practice, but even if it's a little bit odd, you'll be interested in these statistics. So there's been 3 ag census that have the recent ones that have had a question about returning the eroded soil back to the eroded hilltops. And across Canada, about 7% of the farmers report using that practice. It's up from, I think it was 4 or 5% back in 2011, up to about 7% on average now. I think it's between 5 and 9% across the country. That's a huge amount of land that farmers are doing this to. And the funny thing is, no one's doing research on it except this one project we have based in Manitoba. And we also have work that we've started when we've done over the last few years in South Dakota and Minnesota. But this practice has largely been ignored by science and government. And farmers have obviously picked up on this. And as the photo shows here, this is back in France in a document published in 1948, but from apparently the photos are about 1930s, where farmers were doing this. And this has been something that's been done in Europe and Asia for generations, but it's been completely ignored as a soil conservation practice. Well, now that we have very moderate to severely eroded landscapes, it's a practice that desperately is needed. I'm going to give you a bit of background on this practice. So given this increase in interest, I'm going to give you a little background, and here's some images. These images are based on a document produced by Dr. Ellis in a report called The Soils of Manitoba, where he had this wonderful set of hand-drawn diagrams showing roughly what I've shown here. A non-eroded prairie landscape. And so what's interesting about this is on the hilltops, which are very dry compared to the low slope position, you have less soil development. So you start with less soil to begin with. So they're more sensitive to losses of soil. And that's what you would have had in the early 30s on a native grassland. And then he showed back in about 1940, the time he was drawing these diagrams, that once you start to see erosion, it takes this pattern that you've seen in every photo I've shown you, where you lose topsoil from the hilltop, and guess what? It accumulates in the hill bottom. So he was very quick to identify this back in the 30s, 40s, but he never specified what erosion process it was. He just said soil erosion. He may have not twigged into the fact that it was tillage, not wind and water, but he may have very well have realized what it was. And this is even after just a few decades of tillage. You got to remember that much of Manitoba in the 1930s may have only been tilled 10, 20, 30 years. Some of the sites we used in Manitoba weren't broke until 1918. So, and this is what we see when I started in the 1990s, when Alan and others started in soil conservation work. You would see a fairly significant amount of soil loss in these hilltops. At this point, you would see like 50 to 100 centimeters of soil loss on hilltops. And this is clearly caused by tillage erosion. It is not caused by wind and water erosion. There's so many lines of evidence that clearly state that this is tillage erosion, not wind and water erosion. And again, you can see where all that soil is accumulating. This provides a unique opportunity and very substantial opportunity that farmers are very quick to recognize. And so this is why farmers would take that topsoil and put it back on the hilltop. And there's just a few slides. We did some slides just north of Brandon, or some studies north of Brandon with Alan and others at what was the Manitoba Zero Research Association farm. We've also done in other areas of the province. This is from down near Treeherne, and you can see collecting topsoil at the bottom of the hill, putting it on the eroded hilltops, and just a quick summary of what we found in terms of preliminary results. This is from the original set of studies. You get substantial immediate increase in net crop yield over the whole landscape. So on the upper slope positions without losing it in the lower slope positions. And there are concerns about extreme wet and extreme dry conditions, and certainly one crop will respond differently than others. So there's a lot of issues around that, but we found that generally speaking, we get a fairly good return on investment. And that particular study found 3 to 5 years, which is more rapid than any other land improvement practice like drainage and irrigation. So very, very responsive. Our current study, which is ongoing still, we're not finding that kind of immediate response because of some extreme conditions, extreme dry years. Apparently, not surprisingly, in hindsight, doesn't matter how much organic matter you have in the hilltop. If you have no moisture, you have no moisture and you can't grow a crop. Doesn't matter how much organic matter you have. If you don't have any moisture, you're not going to get any crop growing. So that's a lesson learned. Now, the fourth and final point, and I've got a few more minutes here just to summarize a few things. But finally, cultivated land is subject to all of wind, water, and tillage erosion. So I made this point earlier in the presentation as well. Now, although the intensity of these processes vary considerably as conditions change in space and time, so in some cases you may have more wind or water erosion than tillage erosion, or vice versa, all these processes work together in concert, and they can amplify or dampen the effects of the others. So that's that interactions referring to earlier. Consequently, and this is quite contrary to what's currently being done, consequently, integrated assessments of soil erosion is essential, combining wind, water, and tillage erosion and their interactions. Just to give you an idea of what's happened in North America historically, you had a wind erosion camp and a water erosion camp. You had wind erosion research and water erosion research. You had wind erosion programs and water erosion programs, and there was never any overlap in terms of people or programs. Very different cultural setups. Obviously, wind being in dryland environments and water being in more humid environments, but very, very distinct and competitive in terms of research dollars and program dollars. But we have worked fairly hard through support of Ag Canada and the Ag Canada's environmental indicators program, which is now called the Sustainability Metrics Program, looked at trying to integrate all of these erosion processes. And I'm just going to summarize it fairly quickly. So we have assessments of wind, water, and tillage erosion, and models of wind, water, and tillage erosion based on experimental data, modeling data, and using FRNs to validate it, which is unusual. Apparently, most people that have developed models historically never bothered to validate them correctly. But with FRNs, you can, and that ties back into that first major advance. So we have these models and we run them independently, and then we do like a layering of the outputs of it to understand what you get for a net impact in terms of total soil erosion. So we've done that, and we look at these landscape positions. So it's a landscape-based system. It ties into the National Soil Database and the Census of Agriculture, which I made mention of earlier. But all of this information gets rolled up, and we can look at the management effects, the risks associated with tillage systems and cropping systems, and what that means in terms of wind, water, and tillage erosion, and the soil losses you would see by each one of those processes on the upper, mid, lower, and depressional areas. And they do operate differently in different landscape positions. So you really have to have a close eye on the budgeting or balancing of sediment and erosion across the landscape. Okay. And I'm just going to show you a few maps. So I'll give you a bit of background. These are the rates of soil loss that we have illustrating these maps, going from red, which is very high, down to variations of green, which we consider to be low or sustainable. And when we look at it, we have water erosion. This is showing 1981 and 2018, which is the latest ones I got from Lisheng and Ag Canada. And this shows you that with respect to water erosion in the prairies, there has never been much of an issue with water erosion. Now, part of this has to do with map scale. There are always hot spots somewhere in there you just can't see at this coarse scale. But if you look to Eastern Canada, you can see there's like an armpit of water erosion all across the Eastern country. And that's because they do have a lot of water, a lot of 2 to 3 times more precipitation we do in the prairies. And that runs a big risk of water erosion. And for wind, you can see there's more wind erosion in the prairies, really nothing reported in Atlantic and Eastern Canada. And you can see that between 1981 and 2018, there's been a dramatic reduction in wind erosion. And for tillage erosion, it's much more pervasive and consistent across both regions. And that's because it's tillage, it's not climate-based. It has to do with how much soil is disturbed. And so both regions were fairly intensively degraded by tillage erosion historically, in the 1980s, illustrated here. And by 2018 and to today, in Eastern Canada, in Western Canada, it's been dramatically reduced through conservation tillage. So notice you stopped the soil erosion by tillage, but you still have quite a large amount of soil erosion by tillage with the cropping systems used in Eastern Canada. And this is showing you the combination. If you look at all of the processes rolled together, you can start to see that the picture, what is impacting the soil on the land and therefore impacting the farmers and the environment by all of the processes rolled up together. And this is showing you the big trend. And just to point out the trend, the soil erosion has declined steadily by all erosion processes because of conservation tillage. But I do want to emphasize the point, and I think it comes up in another slide, in the last couple slides, that what this means is you have stopped the erosion, the current erosion, but it does not eliminate historical erosion. This is one of the big problems with soil conservation modeling and assessments done historically. And this is another reason why you have to look at integrating soil erosion across erosion processes, but you really have to look at soil erosion integrated over time. And if I have a chance in the last bit, I'll talk about economics, and this becomes quite important. But you have to integrate over the processes, wind, water, and tillage erosion, and they're combined to understand what's going on in terms of the impact on the landscape. But you have to consider what's going on over time. You can't just look at 2025 and say, oh, that's a state of soil erosion. That's a state of the current soil erosion, but it tells you nothing about what happened over the last 40, 50 years. And so any of those images I showed you that are very severely eroded, if someone went to no-till, stopped their tillage, they would be rated as having zero soil erosion. And that may be true, but they have the impact of decades of soil erosion, which is quite significant. Okay, and there's a bit more on that. And I just wanted to point out the cost. I've got no time left. So I'm gonna have to end there, but if there is an interest, I'm just gonna slide forward on my slides here. There's a bit on the cost of soil erosion because there is significant implications for integrating. Integrating is not done as an academic exercise. It's done as a means of understanding the soil loss by all erosion processes over time and looking at the amount of soil organic matter as an indicator of productivity and therefore profitability. And the key thing in all of that, just to summarize in a couple of sentences, is the cost of soil loss back in the 80s was assessed at being about $1 billion a year in 2016 dollars when I did the economic analysis. So keep that number in mind, $1 billion a year back in 1981 in 2016 dollars. It has increased threefold, and it has increased now to $3 billion a year. And that has to do with two things. One, those areas that are continuing to be eroded have gotten smaller, but they're more severely eroded, and they have much higher yield losses. And that offsets all of the benefits of having less soil loss on those historically eroded areas. So there's no net improvement in terms of the soil. But the cost is driven up not by the soil loss, it's driven up by markets. The yields have doubled to tripled. the market value has also increased. So the cost of that erosion has gone up about threefold, even though the rate of soil loss, you could argue, hasn't changed, which is not good news, by the way. It hasn't changed, but the market values has driven that cost of soil loss from 1 billion to 3 billion, which is quite astounding. And I would point out there was a similar study done in the Corn Belt, so the Great Lakes states, and found almost identical results. And in both studies, the primary cause of those moderate to severe soil losses, which are causing the yield losses and the profit losses, in both studies, it was recognized that tillage erosion was the number one cause of that degradation and economic loss. Coming back to that second important research advance, so that's recognize and understand tillage erosion. So with that, Alex, I can end there.